When ambient air humidity leads to rust, mold, and electrical malfunction, it can cause a lot of trouble. Here is a method and a little tool to predict the dew point. There are good reasons why we don't want to have walls getting wet in our house or in our working environment. For instance, it fosters mold, which can jeopardize your health. And in addition, there are a number of reasons why electric and electronic circuits should not get wet. Oxidation or rust degrades the conductivity of switch or battery contacts. In extreme cases, contacts can heat up from this and can even cause fire. Sensitive electronic boards, if they don't get damaged, will show at least malfunctions. Hermetically sealed cases, of course, can help here, however, they are not always applicable. And moisture caused by dew sometimes appears when you do not expect it. Can we somehow measure and predict it? Fortunately, physics has solved this problem. We need to measure air temperature and humidity to compute the dew point temperature on a surface. In order to understand how we can measure or predict the dew point, we need to appreciate a bit the physics behind. But don't worry, I'm not going to explain complicated physics formulas here. You can find these on Wikipedia in case you are interested. We implemented the formulas in our little tool, which I will explain later on. The graphics here, which is derived from the tool, is giving us already a good help to judge whether a surface could get wet or not. We need to know the relative humidity and the temperature of the air. With that, we can estimate the dew point temperature on a surface from this chart. We make some examples. Let's assume that we have an air temperature of 25 degrees Celsius and a relative humidity of 50%, which corresponds to the light green line in the chart. Then we can derive from the chart that the dew point temperature on a surface would be 13.9 degrees Celsius. In a second example, we assume 25 degrees air temperature and 90% humidity, which corresponds to the dark blue line. In this case, the dew point temperature would be already 23.2 degrees, which comes close to the air temperature. As a general rule, we can assume that with higher humidity, the dew point temperature comes closer and closer to the air temperature. It's no surprise that at 100% humidity, the dew point temperature is equal to the air temperature. With our little tool, you can compute your own data and you can predict the dew point temperature in your own cases. The first sheet in our spreadsheet tool gives us a lookup table and the corresponding chart. It is dedicated for a quick estimate, just as I explained it with the examples a minute ago. You don't need to change any values here. The next sheet can calculate exactly the dew point temperature from the air temperature and humidity, which you can insert on the left side here. In addition, It considers automatically a security margin which you can adjust. I choose here 3.3 degrees of Celsius, which is a common assumption for two reasons. First, our air humidity measurement is not very accurate. We need to consider up to 10% tolerance here. Second, even when our temperature measurement is pretty accurate, we need to consider about 1 degree of Celsius tolerance. With the 3.3 degrees Celsius security margin, both uncertainties should be covered. In case the two exclamation marks appear, the humidity is in a critical range and the surface can get wet. In case you can measure the surface temperature with a separate sensor, you can use this temperature directly to compare the computed dew point temperature. In this case, you could lower the security margin a bit, but keep in mind that the inaccuracy of the humidity measurement still remains. Areas of concern typically can be the basement, the bathroom, the garage, or rooms with poor heat insulation. In case you need to analyze a certain area, it is recommendable to take measurements over a longer time period in the critical season. With the third sheet here, you can compute the dew point from a series of measurements. I take now some example values from the last sheet. I recorded them using my little weather sensor project. In case you are interested in the weather sensor project, you will find it in episodes number 8 to 13. I chose on purpose some data where we can see the humidity and the temperature in a critical range. I just copy and paste them to the spreadsheet here. We see the data of 24 hours outdoor measurement on a day with changeable weather. And indeed, we had dew in the evening hours and the next morning was dry. For the case that you want to drive your investigations further, we created the fourth sheet here. It is a bit advanced, but I have to mention here that in case you have a thermal bridge, it is the method of choice to tackle the problem. Not only you can insert a series of air temperature and humidity measurements, you can also insert the temperature of a surface which you can possibly measure in parallel. Furthermore, you can consider separately the tolerance of your air humidity measurements and the temperature security margin. On the right side, there is still for comparison the simple calculation with the 3.3 degrees temperature margin. The insights. We understand now the physics of relative air humidity and the temperature. It defines the dew point temperature on a surface and our little tool predicts it. You can either work with a temperature security distance or you can measure the surface temperature as well for the prediction, which is the secure way to do it. Observing the temperatures and the relative humidity can be very valuable to prevent damage or even health issues. In case you found problems, I strongly recommend to consult an expert in order to discuss the countermeasures. Now, stay tuned And don't forget to subscribe and support the channel. See you soon in the coming episodes.